A very good morning, dear guests, ladies and gentlemen, from Bogor, Indonesia. Sending you a very warm welcome from me, Sarah Simanjunta, your master of ceremony for this today online international conference. Once again, welcome to the International Conference on Mathematics, Statistics, and Data Science 2020 under the theme Optimal Data Utilization to Reach Brighter Future. It is very nice to see all of you again, and we do hope you are enjoying yourself at the conference so far. We welcome you, the Honorable Head Department of Statistics, IPB University, Dr. Anang Kurnia MSI, Head Department of Mathematics, Dr. Insinyur Endar Hanugrahani MS, to all of you invited speakers of Day 2, Professor Pirayut Chansetikul from Kasetsart University of Thailand, Professor Tony Baktiar from IPB University Indonesia, Dr. Chuen Seng Tan from National University of Singapore, Dr. Utami Diasya Fitri from IPB University Indonesia. We welcome you, representative of Indonesia Statistical Association, so-called EC, representative of Statistics Higher Education Forum, Forstat, representative of Indonesian Mathematical Society, Indo-MS, representative of Indonesia Operation Research Association, IORA. To all of you, respected chairperson, distinguished leaders of university, delegations, researchers, and scientists, to all of you students and participants. Ladies and gentlemen, we will continue our virtual tour to meet and learn from so many bright minds and speakers and presenters through this ICMSDS 2020. We now will come to the panel session 3, Professor Pirayut Chansertikul from Kasetsart University of Thailand and Professor Tony Bahtiar from IPB University Indonesia will sharing with us this morning. And this session will lead by Dr. Doni Citra Lesmana, MPhil Math. I will read his CV in advance. Dr. Doni Citra Lesmana, his educational background is PhD Applied Mathematics 2014 from School of Mathematics and Statistics, University of Western Australia. Master of Financial Mathematics 2007 from the same School of Mathematics and Statistics, University of Western Australia, and Bachelor of Science in the year 2001 from Department of Mathematics, Bogor Agricultural University, Indonesia. Without any further ado, ladies and gentlemen, let us welcome Dr. Doni Citra Lesmana. The floor is yours, Dr. Doni.
Thank you, Mrs. Sarah. Can you hear my voice? Can anyone hear my voice?
Yes, yes.
Okay, excellent. Okay, good morning, everyone. It is a great pleasure for me to be the moderator for this session. First of all, I would like to welcome you back to this panel session of International Conference on Mathematics, Statistics, and Data Science 2020, held by Department of Statistics and Department of Mathematics, IPB University. In this morning session, we have two remarkable presenters, Professor Pirayut Chansetikul and Professor Tony Bahtiar. And before we listen to the talk, I would like to give you the brief introduction of the first presenters, Professor Pirayut. Professor Pirayut Chansetikul served as the Dean of Engineering Faculty, Kasetsart University, His formal education was Bachelor of Engineering in Electrical Engineering, Kasarsaps University, Master of Science and PhD in Industrial Engineering, Texas Technology University. His area of interest is in optimization and computational methods. And to get the most of his presentation, I would like to invite Professor Payot to deliver the talk now. Professor Payot, the time is yours.
Can you hear me down there?
Yes, it's clear here.
Oh no. I try to share my screen first. Okay. Good morning. It's my honor to be invited as an invited speaker for the ICMSDS, right, 2020. Thanks for Professor Lesmana for the introduction. Okay. Let's just give the brief abstract of my talk today. Okay. It's referred to the paper that was published, I think, last year, okay, with my former doctoral student, Dr. Pisak Vitya Papakon. He's now currently serves as a lecturer down there in the north part of Thailand University. Okay. So, but I'm not gonna read this article for all of you. Okay, I have some PowerPoint to, but it's just a basic to introduction about me and my co-worker. Okay, and okay, so we go ahead and get started with the PowerPoint presentation. Okay. Actually, I will go to the point that since this is a mathematics and statistics conference, we show you more about mathematical notation so that you all familiar with what I did. Okay. Let's just say that we're trying to solve this problem first. It's a classic production planning under time varying demand, except that the time random demand was represented as a discrete random variable for each period. Okay, you have n, small n as a number period. Okay, and exabyte is a lot size for each period. Okay, and due to the uncertainty of demand, okay, k, the index k represents the scenario that all combination of uncertainty can happen, which can be really large. Okay. You all see the slide, right? Okay. You all see the slide online? I think. Due to the combination of uncertainty, the decision of exabyte here, okay, need to take a risk that sometimes they can fulfill the demand, sometimes they cannot fulfill the demand. And sometimes they fulfill with the inventory, and sometimes they need to have some back order. So the I minus I sub k refer to as the back order, the negative inventory for period I at scenario k. And for I plus is a regular inventory, the positive inventory. So this is actually the very well-known model. But it just when you add the uncertainty for the demand, okay. So and with the combination of the uncertainty, for example, for n period, for each period you have 3 possible uncertain demand. So the scale, the possible all possible value of k can be up from 1 to 3 to the n. Okay. For example, if you plan for 12 weeks or 12 period, you end up having 3 to the 12, okay. That can lead this problem to, let's just say, not only large, a really large scale model. At one point, okay, you're gonna reach the limit of your computation hardware. But that's very hard to say now today because of the advancement of the hardware with the parallel processing and the the cloud computing and all that. But let's just say that we add more combination of the uncertainty. Sometimes the model reach the limit of using the direct software. Okay. So we trying to apply what we call the classic vendor decomposition. Decomposition is like the idea had been initiated for a very long time that we trying to decompose the large problem to a smaller problem, and we expect that the smaller problem can be solved efficiently. Okay. So this is how we decompose the problem. We decompose the X sub I to one problem. Let's just say it's a master problem. And the sub-problem becomes just only I plus and I minus. And we would like to show you that the smaller problem can be easily solved. But at first, doesn't look trivial. Okay, let's just look at how the procedure starts. Okay. First, we try to write the dual model here. And with this formulation, I can initiate any X sub I value. And with I plus and I minus variable, we can always balance this equation. But that's not a very good idea to just randomly just pick up every X sub I value. Okay, you might use as a regular let's just say rule of thumb that you're using day by day in practical. Okay. So X star here, okay, is become the initial variable that you set. Once you initiate X sub I, okay, the remaining variable that you need to solve is only I. It's only I plus and I minus, okay? So in the second stage, once you initiate the X sub I, you move X sub I to the right-hand side because it's already a constant value. Okay? Subtracted with the original right-hand side, D sub I k. Okay. And you rewrite this problem as a dual model. Okay, so the right-hand side becomes the objective for the coefficient for the in the objective function of the dual model. And for each constraint, you have y sub I k as a dual variable. And for this constraint on the left-hand side, you can transpose this and rewrite, refer to the variable y sub I k using this formula. And the coefficient for the I minus and I plus for the original primal objective value or objective function can be the right-hand side here. Except for when I equal to n, you don't have n plus 1 anymore. So when I equal to n, you can see that in the last one, you have only one constraint here. You don't have y sub n plus 1k. Okay, so this is a dual form once you already decompose the problem. Okay, so the first stage is you initiate the x value, and then you get the remaining variable I plus and I minus, and you move it, write a dual model. Okay, once you already write a dual model, if you solve this problem, which is not trivial, when you look at this formula, it's not trivial. And when you solve it and you did get what we call the optimum solution, we add one more index of j as a number of iteration, because this process you need to iterate it before you can reach what you call the strong duality, when primal and dual meet the objective meet each other. Okay, so j is the iteration number. Okay, and you can move this to the original primal problem. Okay, so this is actually the objective for the dual for the dual problem, because if you remember that x sub I is already initiated, actually it's a constant here in the dual model. So this becomes the objective for the dual problem. But with the weak duality theory, you know that the objective function for the primal problem has to be they cannot exceed the objective value for the primal problem. And this is already well known, just an application from the vendor decomposition problem, that it becomes the sub-problem to find the new x. You remember that y is solving the dual problem. And then once you get the y value, you want to get the new x value, you're using this as a weak duality theory to set up this problem. And sometimes they call optimality cut model. And certainly, if you know Bender decomposition, there's some way that you might face some infeasibility. So there are two types of cut, the optimality cut and infeasibility cut. But in this case, based upon the model, we don't have to worry about infeasibility cut. So you need to solve this problem to get the new x by value, okay? And repeat the process again, okay? Once you know the x, you're going back to the primal model to replace the x from the previous iteration and recompute the y again with j equals j plus 1, okay? So let's go back here. Once you get the new y, you add this as additional constraint, and you stop when t is convergent, okay? And when t and c here, okay, let's just say the objective for the dual problem is equal to the primal. That reach the strong duality theorem. That's already well known if you know Bender decomposition. Okay? So just an application to solve this problem. But the key problem is that how we can solve this problem efficiently. Okay. It doesn't look obvious here, but certainly have some recurrent relation, yi sub k minus yi plus 1 sub k, except here. Okay. So we need to develop some, actually Apisak, my student, okay, is a guy who tracked down and be able to develop this algorithm effectively, okay. So we're going to do that, how we can solve this problem, make this problem to be solved as a trivial solution. Okay. First of all, okay, we need to identify, this is the original model. Okay, we identify, reformulate the problem by identifying the new variable we call u sub I k, and this one also, u sub I k and plus this relationship, okay, y sub I k. The relationship between u sub I k and y sub I k and y sub I plus 1k, and replace it to the original model. Okay, so you can see that this is the two constraint. You replace y sub I k with y sub I plus 1 plus u sub I k, and this one minus u sub I k. So this one cancel each other, so you get only u sub I k as a lower limit and upper limit of g sub I k, h sub I k, which is the coefficient for the objective function. And for the objective function, this is very interesting. Okay. Once you replace u sub I k, okay, with here, this one just says expansion for all I. Okay, and then you start to replace this for each y sub I k. Okay, for this one u sub I k, this one u sub 2k, u sub 3k. And again, you know that y sub 2k can be used this formula to replace also, okay, for each of these. So the term can be keep expanding until you reach the limit of I, which is n. The last one is u sub nk. You have no more expansion for it. So with this one, u sub 2k, you can keep expanding until you reach y sub nk. U sub 3k also, you can keep expanding until you reach y sub nk. So you end up getting, reformulate the problem by reformulate the y to become, with the new variable u, except y sub nk here. Because y sub nk is only individual and independent constraint. Okay. So in the next process, you're trying to regroup the term. This is a basic algebra, you know, for all you mathematicians. We see that u sub 1k, okay, we become only the objective function here, but u sub 2k, you have these two terms. U sub 3k, you have these two terms, okay? These two terms for u sub 2k, the cumulative term. And u sub 3k, up to n minus 1, you have cumulative from d sub I k minus x sub I up to I equal n minus 1. So this make it to rewrite, okay, you can see that we reformulate this problem with from y sub I k, I equal 1 to n minus 1 to u sub I k, and end up having only the last variable that still remain, which is y sub n k. And if you look back at the formula here, okay, we reformulate this problem to this, And u sub I k is a bounded variable and y sub n k with this relationship. So you can see that this problem becomes trivial to solve. You don't need any software to solve this problem because you just look at the coefficient that multiply to u sub I k. If it's positive, since the objective is to maximize this function, if u sub I k, if this coefficient that multiplied to u sub I k is positive, you just pick the upper limit. And if it's negative, you pick the lower limit. You're going to end up having the maximum value of W. So this is what we call special purpose algorithm we add to the model. Okay. And you know that with this transformation, you don't need any software. You can write your own code to solve this problem. It becomes a trivial solution. Okay. So I just code this, okay, using MATLAB and also with Apisa also, we helping each other to code some part together. And luckily, Kurobi is available in MATLAB at that time. Kurobi, as you know, that is an extension of the CPLEX for the Excel, okay, for the Excel format. But it become available with the as a object in the MATLAB programming. So we use MATLAB environment to solve this problem. As you see, this is the numerical results. And actually, the problem consists of 6 periods, okay, and 6 period problem, okay, which n is equal to 6. This is the number of scenario, which is k. The running number of k is from 1 to 100, 500, and you randomly generate d sub by k based on any uniform distribution assumption. Okay, so the size of problem start increasing, but it's actually still don't have any integer constraint. But you can see that Kurobi at one point start to increase. Actually, you can test this program up to a multi-million variable because as you know that nowadays we can solve linear programming a very large scale up to a multi-million variable using the current state-of-the-art hardware. Okay, but the Bender approach, okay, with the reduction of the special purpose algorithm, adding to solve the sub problem, I think that we achieve that you can look at the graphical solution here, that the Kurobi have start increasing when they start reaching the uncomfort zone because due to memory requirement and within the hardware. But for the Bender decomposition, since we already reduced the model to only X, you know that for sub problem we solve only X, we erase all the I. Because all the I, we solve the dual model to get the dual variable Y sub I K. So we don't need any much memory to solve this problem. So that's the very first result, okay, for us, okay. I'm going to switch back to the original paper here. Okay, that's a basic idea. Actually, we wrote that paper in Thai language for a Thai journal. But for the publication here, okay, we add what we call, I'm going to try to be brief here. I think that it's open access, okay, this journal. So you can get into the journal website and download it for free. Okay, so we add what we call the fixed charge problem to the original Wagner-Witten's classical dynamic loss sizing under time varying demand. You know that we add with this variable PT. But actually this one just to make a sub problem a little bit more difficult because you need the mixed integer programming routine to solve it. But again, with this X variable, we add to the optimality cut model. But certainly the sub problem of I plus I minus still hold the same concept that I already showed. Okay, so this one is already show the concept, the previously that I just mentioned to you. So the result is not, this is just the same as I showed you in the PowerPoint, okay? And so this one, he just comparing with the mixed integer linear programming, which is a Kurobi in this case. And we now know that when you increase scenario, but you can see that for for not a very large problem. This one is only 5 period problem here. Okay, and you can see that at one point, okay, BCS is a vendor decomposition, okay, that with special purpose algorithm that all the problem that let's see for the graphic here, okay, 5 period, 15 period, 10 period, and 20 period. Okay, this one has more experimental results because of the reviewer request to improve the paper at that time. Okay, so you can see that the processing time of our method, okay, but it's not proven in terms of algorithmic theory yet. Okay, it looks like a linear curve. Okay, here based upon the experimental results. Why this one is a case of MILP that show not to become linear. Okay, so actually the difference between the previous presentation and this paper is that this paper we add some of the fixed charge constraint, okay, to the original time dynamic loss sizing. Okay. Do I have a few minutes left? I think I'm going to show you what we are continue working on a little bit about what we are doing now. Okay, we are expanding this concept to solve this type of problem, which is okay, thank you. We expand this problem to add with the cutting stock problem with discrete time varying uncertain demand. And you know that the cutting stock problem has some transformation from the original standard size to you cut the width size to a smaller width size. And without any uncertain demand, it's already a large scale problem. We call the initial programming problem with too many variables because the number of variables rely on the all possible cutting pattern. Let's just say, okay, I don't have much time. The same concept can be applied here. But to work it effectively, you need to add this work with the column generation procedure because the original model has so many variables instead. So this work is a combination of the previous work with column generation to work on. And I think that we just go to what we call let's just say that we already have some initial experimentation results here, okay, with period, number of period, if we want to do. You have to know that the cutting stock problem is a lot more difficult than the direct production planning problem. And it took a much longer time to solve because of the initial variable. But at this stage, okay, I'm going to conclude overall that the finding that we found so far is that certainly when you add this vendor decomposition with special purpose algorithm, they're going to work well with large scale problem, which means that when you have a large number of scenarios. At one point, the direct column generation cannot work. But this problem is more difficult than the previous problem because of the initial restriction. We have worked on some heuristic for the heuristic routing algorithm when the solution reach the optimum solution under the initial constraint relaxation. Okay, and our paper have already been accepted for the International Journal of Mathematics of Operation Research, but that was scheduled to publish maybe next year. Okay, so. And I cannot share it with you right now, but if you are interested for this paper, you can, give me a call, contact with the organizer about my email address and anything. I'll be willing to. Right now, I have the draft that haven't assigned the page number yet. If you are interested to read it, I'll be willing to send it for each of you directly, but I cannot do it publicly, because this journal is not the open access. Okay, I think I used. I'm not sure you over time or not, Dr. Lesmana. So I'm going to
have another 1 minute, Prof.
Okay, I'm going to stop my presentation and would like to hear some question or comments or some recommendation from anybody who attend this session. Thank you very much.
Okay, thank you, Professor Payot. This is very interesting topics and yet realistic because when producing products, I believe that the producer will consider the demand function first. This is the most important information for the producers. But in fact, we still don't know for sure the demand. So by putting uncertainty into this model, it makes the model becomes realistic and more realistic. And I believe there will be many questions later, but we will postpone the question and answer session into the last part. Before that, we will listen to the second speaker first, Professor Tony Baktiar. But before we listen to Professor Tony Baktiar, let me give you a brief introduction about Professor Tony Baktiar. Okay, Professor Tony Baktiar serves as a faculty member at the Department of Mathematics at IPB University. His formal education was Bachelor of Science from Department of Mathematics at IPB University, and then Master of Science from Department of Control, Optimization, and Stochastic, Delft University of Technology, the Netherlands, and PhD from Department of Information Physics and Computing, the University of Tokyo, Japan. And he is also a research fellow in International Center for Applied Finance and Economic, IPB University. He was also an active member in some society membership, in Institute for Operation Research and Management Science, Society of Instrument and Control Engineers, Indonesian Mathematical Society, and also in Indonesian Operation Research Association. He was awarded with SICE Young Authors Award in 2004 in Sapporo, Japan. Okay, to Professor Tony Baktiar, the time is yours.
Okay, thank you, Pak Tony. I will share screen. This is our screen.
Yes, I can see it clearly.
Sorry, this screen shared by me or?
Prof. Tony, will you share it by yourself or the
Okay,
host will?
I will share by myself.
Okay.
Okay, everyone see the slide here? Okay, good morning, everyone. First of all, I would like to thank the committee of this conference for providing me valuable opportunity for sharing my research, our research actually, because this is the joint work with my colleagues, Ihza Rizkia Fitri, Farida Hanum, and Ali Kusnanto. The title of my talk today is a mathematical model of pest insect control. Okay, the theme of my talk is actually the modeling and also possible control for the pest insects that have flourished our crops in agriculture system. And there are some motivation or some background that this topic is very important because pest and plant disease have challenging our food security and also causing a very high loss in crop production. For instance, in rice, we lost 30%, maize about 20 wheat, soybean, and also potato. Globally, this loss is about 470 billion US dollar. And the damage caused by pest, insect and disease will give a bigger risk in any tropical country, especially in Africa and Asia. And also we know that the global warming will provide more burden because the warmer temperature will accelerate the consumption rate of the pest. And based on the simulation, 1 degree increase in the temperature will project an increase of 10 up to 25 of economic loss. So to deal with the various risks in agriculture system, it is necessary to develop and implement proper strategies, particularly in agriculture, to ensure that the economic profitability and food security is saved by this effort. So in this work, we adopt the integrated pest management or IPM to develop our model and control mechanism. Actually, IPM promotes the use of the integrated use of chemical and also physical and cultural and also biological tools in combating the pest and disease. At least there are 3 key components. The first one is prevent the buildup of the pest. The second one is monitor crops for pests and natural control mechanism. And the third one is intervention when control measures are needed. In fact, our work will lay in the third components, namely the intervention when control is needed. So first we will model the pest and plant interaction, and then we will propose some control mechanism. So we know that IPM is promote some mechanism that's efficient and sustainable in environmental application of control measure. So there are some integration between biological, chemical, and also cultural and physical. But in this talk, we will consider some biological control to regulate the pest insect. There are many mechanisms or control measures available, such that natural enemies, the release of natural enemies, and then mating disruption, mass trapping for the pest insect, and the use of green insecticide to control the growth of the pest. And we also already know that mathematical models play notable roles in approximating, predicting, explaining, and analyzing the pest crop interaction. At least there are 2 directions in mathematical modeling to support the pest control initiative. The first is, of course, laid in the building of a model to describe the population dynamics. This direction will produce some models, even for single species, multi-species, and any other more realistic characteristic. And also the modeling showed the interaction among plants, insects, and predators. And usually this study will produce as the result, such as a stability analysis, which is consists of the expression of the basic reproduction number, bifurcation analysis, and the sensitivity analysis. The second direction is the development of pest control model, which enable us to intervening the model. I mean, the model can intervene the interaction between pest and plant. This is include the use of pesticide or insecticide, the release of sterile insects to natural predator, mating disruption, and so on. And also, this study will give the optimal control strategies. So our talk will be in the second direction, namely the first the modeling and control. We will evaluate some control mechanism to intervene the dynamical of the pest and plant dynamic. Okay, this is the objective and outline of our talks. The first one, we propose the comprehensive IPM, Integrated Pest Management Model, to optimize the simultaneous application of biological measure to control the pest dynamic. And the second one, we aim to derive the optimal intensities of mating disruption, green pesticide, and infected plants removal. So in the next slides, we will show you the control measure we use, our compartment model and the assumption, optimal control problem, and the optimality condition. And we will provide the illustrative example. And also we make some cost effectiveness analysis just to know which is the best strategies. Okay, as I mentioned before, we will use 3 control measures here. The first one is mating disruption. And the second one is the use of green pesticide or green insecticide. And the third one is infected plants removal. Okay, I will briefly explain in the next slides. Okay, this is the mating disruption. Actually, for mating, the female insect release some sex pheromones, and then the male will follow the track of this pheromone to find the female insect, and then the mating is happen. And we mean by mating disruption is direct control technique by the release of synthetic sex pheromones. This synthetic pheromone is deployed by dispenser. Here we have some dispenser, or by spraying aerosol system. This is of course a fake pheromone. The amount of this synthetic pheromone is very high, higher than that produced by female. And because of that, the male will be confused and they cannot find any female. So the mating is not happen. Okay, this is a mating disruption. And the second one is the use of green insecticide. This is a special insecticide with we call bisacylhydrazine. This is this insecticide only kill larvae and very eco-friendly. And the last control measure is more physical. I mean by removing the infected host plants. Like for instance, in the bananas, we will give injection of herbicide to kill some black cicatoga. Or in the apple plantation, we just destruction the trees of apple with scrap. Okay, this is our compartmental model. Actually, this is a very generic model. And we would like to show you some characteristics of this model. First, we divide the compartment into actually two population, the pest, insect, and the plant. But for the insect, we divide by larva, the yellow box here. This is a larva, and the orange is non-infectious insect. So this insect cannot spread the disease. M is for male. Y is the unfertilized, and F is fertilized. Fertilized means this insect is ready for mating. And the red one is infectious insects, pest insect. They can transmit some disease to another insect and also to the plants. The green one is susceptible plants. This is the healthy plants. And the magenta is the infected plant. So we have a rich characteristic of the model. We distinguish between larval and adult insect, male and female. Among females, we divide by fertilized and unfertilized, and also susceptible and infected insect. And for the plant, we divide by healthy infected plants. And there are some assumptions we use. First, the pests and plants are unspecified. Of course, this is a little bit not ideal. Ideally, we propose a model based on a real case, but this is still a theoretical study. So we try to propose a very generic model. And then if we have some case of pest attack, then we can modify our model. So the population of larva grows under saturation. I mean by this equation, this is like growth with capacity, environmental capacity, but not like that. We call this the saturation effects. And larva will grow to be mature, susceptible insect with some kind of rate. So for L to become a male or or female here. And the very unique characteristic is we consider mating probability here in this row here. So the mating probability is completely defined by the ratio between the male and female. If the male is much higher, is the number of male is much higher than the female, then probability of mating is certain. So we put the value by 1. But if the male is less than the female, then the sex ratio is the mating probability. There are some assumptions left, but I will not explain one by one. And this is our mathematical model. We have 9 differential equation, non-linear path ordinary differential equation. L is for larva and M is for male susceptible and so on. We can see that there are a very complex interaction between male and female here. And also we have some control variable, some control measure, which is the U1 is the use of green insecticide. I mean, if we apply this green insecticide, then the population of larva will be reduced. and we have a mating disruption here, U2. U2 is applied to the female susceptible or infectious. So the application of a mating disruption, the spraying of synthetic sex pheromone will imply to the dynamic of female, unfertilized and fertilized female. And we have a U3 here. U3 is the removal of infected plant. So PI is the density of infected plant. So we remove some of them to reduce the possibility of infected for another plants. So this is our optimal control problem. We would like to determine the optimal intensity of our control measure, how much the killing rate of larva population. I mean, how much green insecticide we have to apply, and how is the proportion of sex pheromones, synthetic sex pheromones, and the third is how is our removal rate. So we have to determine the intensity such that maximize the healthy plants biomass. This is the performance index or cost to be maximized. The first term is the healthy plant biomass, and this is the control effort. So by maximize, we should maximize the healthy plant, and in the same time, we reduce the control effort. So maximize the healthy plant and minimize the control effort, because of course, we would like to control something with the minimal cost. And this is the optimality condition. Actually, we use a very standard procedure, namely the Pontryagin maximum principle. There are 3 or maybe 4 conditions which should be satisfied. The first condition will produce the model itself. We call it the state system. We have 9 conditions. This is the original model. And the second condition will produce the optimal control, U1 star, U2 star, and U3 star. And the third condition will produce, namely the adjoint system. This is very long system of differential equation. I don't put the expression here. And we can see that these 3 blocks of system should be solved simultaneously, because U1 is still depend on L, and also U2 depend on YI, and also P4, P6, and so on. So we have to solve 3 blocks of system simultaneously. And this is our numerical methods. Our numerical method is very unique because of its characteristic. For the state system here, we have an initial condition, because in the beginning we already know the number of infected, of susceptible, of the larva and something. But for the adjoint system, we have a terminal time condition. Why we have this terminal time condition? Because we do not specify what is happen in the end of our control period. To handle this kind of characteristic, with some of them have an initial condition and another have a final time condition, we have a combination of Runge-Kutta algorithm and also extended sweep method. For the forward is a state system. We solve the state system forwardly by using a Runge-Kutta algorithm. But for the adjoint system, because they have a terminal time condition, we use backward extended suite method. And then we got the numerical solution. And this is the illustrative example. We start with density of population of larvae by 100 and non-infectious male by 30. This is just hypothetical data, of course. And also we consider a few initial density of plants here. Healthy plant is 120 and infected plant is 30. And we evaluate 5 scenarios in control. The first one, we consider a situation without control. I mean, we do not use a green insecticide, U1 is 0, and we do not spray the sex pheromone, U2 is 0, and we do not remove all infected host plants. So U3 is 0. This is the no control strategy. And we propose 4 strategy based on the use of control, A, B, C, D. For instance, strategy A is using all controls available. The rate is between 0 and 1, and we will leave the model to decide the optimal value. The P1 is only use the first 2 controls. The strategy C is use the first control and third control. And we also consider the bounded control here. So we consider only between 0 and 1. And this is some simulation result. Please note that the dust line here is no control strategy. So without control. And sorry, and this is for A, B, C, and D. So we have 5 lines here. This is the A, I cannot see the, okay, what we would like to see here is the larva and infectious insect here. We can say in general that strategy A, B, and C, which exploit green insecticide to kill the larva, succeeded in reducing the explosion here. If we have no control, then the population larva is in the dust line. But if we use a Bach green insecticide, then the explosion will be altered. And the second picture here is for the infectious male. We can see that all control strategy can reduce in a certain number the population density of male infectious. And this is for the unfertilized female. And the last figure is for the infectious fertilized female. And this is for infected and healthy plants. We can see here in the left figure that almost all of strategy, except the strategy B, can reduce the number or the density of infected plants. And for the right picture, we can see that all strategy with a certain effectivity can improve the biomass of healthy plant. But the difference between strategy is not too much. And of course, if we have 3 control, then we have to pay more than we use only 2 controls. And this is the interesting one, the probability of mating. The probability of mating is depend on the number or in the ratio between male and female pest insect. The dust line is without control, and where without control, the switching between male scarcity and male abundance is about 5 days. But if we make control measure, especially by strategies A, B, and D, and then the switching between male scarcity and male abundance will shift to the right for a few days. And this is the optimal control, how we should apply our control. This is for strategy A in the top corner, top right corner here. So we have to, if we apply all available control, then we have the U3, the removal, full capacity at the end of the control period. In this case, we consider 80 days of the control period. But for the U1 and U2, this is the green insecticide and mating disruption, we only apply in the full capacity in 50 days. And then we reduce the intensity. And this is for the strategy D. This is the strategy C, and this is the strategy B. And of course, it is difficult to compare among strategies because each strategies have their own cost and benefit. So in this slide, we calculate how much benefit and how much cost they use or they incurred. Benefit is the difference between biomass of the healthy plants under certain strategy and without a control strategy. And the cost of the control, okay, is just the integral of the summation of all control used. So we use incremental cost effectiveness and a ratio I share to calculate the ratio between benefit and cost. And we can see that the strategy B, by using green insecticide and mating disruption, provide the most cost effectiveness. Strategy B successfully decreased the number of infectious insects by almost 16%, and the total number of insects, including larvae, by 14%. And the number of the density of the healthy plants biomass is increased by 11%. So I think this is our conclusion. So we have proposed a generic model for plant-insect interaction. We also evaluate 3 control measures, namely the use of insecticide, green insecticide, the mating disruption, and removal. Of course, in the future, we have to specify the name of the pest and also the plants. Also, we realized that this theoretical study needs a validation through field experiment to verify the model and parameters. Okay, this is the end of our slide. Thank you very much, Pak Doni.
Okay, thank you, Professor Tony Baktiar. This is very interesting topics, yeah, because it is considered as an environmentally friendly method to prevent the insect, yeah. Even though it also can be considered as a cruel method because it prevents the insect to do the mating process. And now we already in the session of question and answer session. If all of you have any question, you can simply click the raise hand button or just type the question in the chat section. We already have one question here for Professor Payot. Yeah, I think it's already here. Yeah. Oh, we already have some question. The first question for Professor Payot. You mentioned that Bender's decomposition combined BCS require shorter processing times compared to the simple mixed integer linear programming. In a case of large-scale problems, what if your BSC approach is applied to small-scale problems? What other advantages of your BSC approach? Professor Payot, please give your...
Okay. Can you hear me? Okay.
Yes, yes, I can hear you.
To answer the question, certainly with the advancement of the hardware nowadays, you can. I think that you better start with solving directly using the software first. But at one point, when the number of all possible scenario for the uncertainty increase, at one point, I think the result already showed that there'll be break-even point. You need to find out that. So you start for small scale, you start with the direct formulation and solve it using software. But when you reach some level that the software having some trouble, they enter their uncomfort zone. Okay, so you start switching to use the BSC approach can help you to solve larger scale problems. Thank you.
Okay, thank you, Professor Payot. And we also have a question for Professor Tony Baktiar from Pak Bagus Sartono. Thank you for a very comprehensive talk. You mentioned that it is a theoretical approach and a generic model for unspecified species of plants and pests. Suppose that we would implement your approach, what kind of data that we should collect in terms of what variables to be measured and recorded, and how long should be the observation conducted? Okay, Pak. Professor Tony Baktiar, please.
Okay, thank you, Pak Doni, and thank you, Pak Bagus, for the question. Actually, in our model, we have more than 40 parameters should be decided the value. For instance, how much the intrinsic X laying rate for the larva, and how is the intrinsic plant growth, and how about the transmission rate of pathogen from infected plants to susceptible, and how is the transmission rate of pathogen from infectious insect to susceptible plants. This is the transmission rate between insect and also insect and plants. And also, for instance, the number of females that can be fertilized by a single male. In our case, we assume that one single male can mate with 2.5 females. Of course, if we consider a different type of insect, then the ability of mating is also different. And also, it is possible to a bit modify the life cycle of the pest, because different pests have different life cycle. And about the control period, yeah, this is of course depend on the type of insect. This is included in the life cycle. So when we should start the control, and when we should stop the control, is very important. In our case, we just take 80 days based on the reference, not by field experiment. That's Pak Doni.
Okay, thank you, Prof. Tony Baktiar. Any other question from the audience? Not yet. Okay, I have a small question for Professor Tony Baktiar. I would like to know whether there is any initial condition that is considered as unsecurable. I mean, is there any condition for the initial condition, yeah? Regardless of the strategy, in the end, all the crop will be damaged.
Okay. Actually, the initial condition, for instance, for the initial density of insect and also initial density of plant is very crucial. In this case, in this talk, we just take a hypothetical data, but actually the correct mechanism or the correct procedure to define the or to decide the initial number of population is by using what we can say that by first we consider model without disease, just the interaction between pests, and then we run the simulation to know the stable or transient level of density, and then we can take that number as the initial condition for the pest, for instance, and then from that we apply the control, and also we include the disease. That's the actually the correct procedure to decide the initial condition, not by some assumption or by using hypothetical data. That's what I know.
Okay, thank you, Professor Tani. So basically, we can also do simulation with the model, Prof, to check whether some kind of initial condition will result in to see the final situation about the crop, right?
Yes, of course. If we use a different kind of initial condition, the result will be different. But yeah, how much the difference is significant or not should be checked by running the model.
Okay, thank you, Prof. Any other question from the audience? Okay, I think that's all the question from the audience, Prof. And also the time is over. And I would like to once again to thank the two remarkable presenters for the talk. This is very interesting, and I believe that it will be beneficial for all of us. And for this, I would like to return this session to our MC, Mrs. Sarah Simanjuntak. Thank you.
Thank you very much, Dr. Doni Citra Lesmana, that already led this panel session 3. We thank you very much to both of you, distinguished Professor Payot Chansatiko from Kasetsart University of Thailand, and to you either Professor Tony Baktiar from IPB University Indonesia for sharing your knowledge and practical sharing this morning. Ladies and gentlemen, we have listened very attentively to very tough, provoking presentation, very informative indeed from the both professor. We now invite Head of Department of Mathematics, IPB University, Ibu Endar, to deliver the token of appreciation and the certificate to both of the invited speakers, either to the moderator. We welcome you, Ibu Endar.
Okay, thank you, Miss Sarah, for the time. And good morning, everybody, especially our distinguished presenter this morning, Professor Payot and Professor Tony Baktiar. On behalf of the organizing committee and also on behalf of IPB University, I would like to present you both our distinguished presenter this morning, the token of appreciation from the committee. Can the committee share the token? Okay. presenters first, maybe. Thank you. Okay, this is the our token of appreciation for our first speaker this morning, Professor Payot Sansetiko from Kasetsat University. Thank you for sharing us with your research, your expertise, and also sharing us with your networking. Hopefully that we can cooperate again with you in the future to make both of our universities be better in the future. Thank you.
Thank you very much. Thank you very much.
Dr.
My
Payot,
honor. My honor.
you can say a few words.
So, no. Thank you, sir. Thank you.
Okay, hope you enjoy it.
Yeah.
Okay. And the second token of appreciation goes to Professor Tony Baktiar. Professor Tony Baktiar is a member of our university. We know how good you are in your field of observation research, and we thank you for sharing with us, all the participants of this conference, about the result of your research. This is the token for you. Thank you once again, Professor Tony. You can say a few words.
Okay, thank you, Bu Endar, committee, and all participants for providing me with this very valuable opportunity. Thank you very much.
Okay, you're welcome. And the token of appreciation also goes to our moderator for this morning's session, Dr. Doni Citra Lesmana, for chairing the first plenary session this morning. Dr. Doni is also the member of our university. We hope that we can cooperate further in our future activities. Thank you, Dr. Doni.
Thank you, Bu Endar, and thank you all the committee for the hard work.
Okay, that's closing the first session, first plenary session. Thank you for you all for your participation, and I will give back the time again to the MC to the next step of the meeting of the conference. Thank you.
Thank you very much, Ibu Endar Nugrahani. Thank you, all distinguished persons. Distinguished guests, ladies and gentlemen, as mentioned on the program book, that by 9:30 a.m. Jakarta time, we come to the parallel session. There will be 6 topics to discuss in 6 different rooms. Ladies and gentlemen, kindly rename your ID on your each screen using the format room_sessions _ either you are presenter or audience and _ your name. For example, as we now will come to session 3 and you will discuss in room A, and my name is Sarah, then I will write A_3_audience_Sarah. Or if you are the presenter and you will present on room B, then you can write B_3_presenter, and let's say your name is Bunga. The parallel session 3 will divide into 6 rooms. Room A will discuss under the subject data collection and will lead by Mr. Aam Alamudi. Room B will discuss under the topic time series, will lead by Mr. M. Nur Aidi. Room C will discuss either on the subject of time series and will lead by Ms. Cici Suhaini. Room D will discuss about generalized line model, will lead by Mr. Doni Citra. Room E will discuss under the topic machine learning, will lead by Mr. Tito Julianto. And room F will discuss under the topic mathematics and will lead by Mr. Payan Sianturi. But before you go to your each room, ladies and gentlemen, just a quick reminder of our agenda that after the parallel session 3, by 10:55 a.m. Jakarta time, please join back to the main room as we will continue our program to the panel session 4. Dr. Chun Seng Tan from National University of Singapore and Dr. Utami Diasafitri from IPB University Indonesia will sharing with us. Thank you very much. Enjoy the scientific discussion and see you again at 10:55.